This is not a simulation. These are the final images sent by NASA's DART spacecraft. That bright rock is Dimorphos, an asteroid moon about 560 feet wide. Every frame gets closer because the spacecraft is aimed directly at it. Then the image stops. The camera did not fail. The entire spacecraft hit the surface at roughly 14,000 miles per hour. NASA destroyed it on purpose. The goal was not to blow the asteroid apart. It was to answer a much more useful question. If a dangerous asteroid were headed toward Earth, could a small spacecraft change its path enough to make it miss? The collision worked. But the strangest part is that the spacecraft itself was responsible for only about half of the final push. Dimorphos was never a threat to Earth. It orbits a larger asteroid named Didymos, making a natural two-body clock that telescopes could measure before and after the test. Before impact, Dimorphos took 11 hours and 55 minutes to complete one orbit. NASA did not need to move it a dramatic distance. The mission only needed to change that clock by at least 73 seconds. That is the key idea behind kinetic impact planetary defense. You do not wait until an asteroid fills the sky and try to destroy it. If you find it years in advance, a tiny change in speed can accumulate into a large change in position. By the time the asteroid reaches Earth's orbit, Earth is no longer at the crossing point. Planetary defense is less like stopping a bullet and more like changing a train's schedule while it is still hundreds of miles away. DART was roughly the mass of a small car. It launched in November 2021 and spent 10 months traveling toward the Didymos system. During the final hours, controllers could not steer it by hand. Radio signals took too long, and Dimorphos was a small moving target beside a much larger asteroid. DART's camera and autonomous navigation system had to identify the correct body and guide the spacecraft into it. In the replay, Didymos appears first. Then the smaller Dimorphos grows from a few pixels into a world of boulders. The last complete image was taken about 2 seconds before impact. A final partial frame shows a strip of surface less than a second before the spacecraft was destroyed. At mission control, the screen went black exactly as planned. But DART had already released a separate, shoebox-sized camera satellite named Cube. It flew past after the collision and photographed an enormous cloud of rock blasting away from Dimorphos. That cloud was not just debris. It was the hidden engine of the mission. When DART hit, it transferred its forward momentum to Dimorphos. But the collision also excavated rock and launched it backward into space. Newton's third law says that throwing material one way pushes the remaining body the other way. It is the same reason exhaust accelerates a rocket. In this case, the asteroid supplied the exhaust. Scientists call the extra shove the momentum enhancement factor. The amount depends on what the asteroid is made of. A hard, solid body and a loose rubble pile do not react in the same way. Images showed that Dimorphos is a weakly bound collection of rocks. The impact released enough material to form a long tail visible to telescopes in space and on Earth. The latest analysis puts DART's momentum enhancement factor at about 2. That means the escaping debris roughly doubled the punch created by the spacecraft alone. The asteroid became part of the deflection system. The result was far larger than the minimum success target. Dimorphos' orbit around Didymos became about 33 minutes shorter, not 73 seconds. Humanity had intentionally changed the motion of a celestial object for the first time. Then, in 2026, researchers reported an even smaller but more remarkable effect. DART had not only changed Dimorphos' orbit around Didymos, it had measurably changed the path of the entire two-asteroid system around the Sun. Their 770-day solar orbit changed by just 0.15 seconds. The change in speed was only about 1.7 inches per hour. That sounds useless. For an emergency mission launched at the last moment, it would be. But given enough warning time, a tiny velocity change keeps adding up. A future impactor would not need to push an asteroid across the solar system. It would only need to make the asteroid arrive at one point a little earlier or a little later than Earth. DART did not prove that every asteroid can be deflected this way. Different sizes, structures, and warning times would require different plans. It also did not endanger Earth. NASA says the test target was not on an impact path and the mission could not put it on one. What DART proved is simpler. Humans can deliberately move an asteroid, measure the change, and use the asteroid's own debris to make the push stronger. The final black frame was not the end of the experiment. It was the first time planetary defense became something we had actually done. If you like decoding the hidden mechanism inside real footage, subscribe to Why It Spiked.